Hi, my name is Dheer Moge, and today, along with my colleagues Arth and Subin, we will be talking about object store performance, what it takes to benchmark it, how to troubleshoot it, and how to improve the performance. Three of us have been involved since the inception of the object store product in Nutanix, and hopefully you will find the journey that we have had useful for your work. As part of agenda, we will first talk about the relevance of object store today, the what and the why it's finding increasing adoption in data centers on premises. And next, we will move on to the main course of the presentation, which is how do you benchmark an object storage system? How is it different from other typical storage systems? How do you troubleshoot it? What are the tools that you can use? And in the end, we will share some of the results and how we improve the performance based on some of these findings. So let's first look at what of object storage. Object storage or storage today can be consumed primarily in three different ways. The first is block storage, where storage is consumed as blocks over LUNs. There is no namespace. You only consume LUNs at offsets and length. Typically, the protocol which is used to consume block storage is SCSI or iSCSI, and it's popular for applications which use structured data, where the data is formatted in table spaces like a database, like a relational database, where the latency is very important and the database is willing to do all the hard work of managing the storage. Next comes file storage, where namespace is hierarchical in nature and is organized as folders or directories and files. Typically, over the network, files are consumed using NFS or SMB protocol. You can also consume files locally using a local file system like NTFS or ext4. And this is typically used for structured and semi-structured data. And lastly, object storage, which is a new kid on the block, relatively speaking, uses a flat namespace where the storage is organized as buckets and objects, just two levels. And the access protocol is HTTP REST APIs. S3, which is a protocol from AWS, is the de facto standard here, and which is quite prevalent. And this is used for semi-structured and unstructured data. With evolution, the lines between file storage and object storage are increasingly getting blurred in terms of the use cases. Next, look at some of the use cases for object storage, or what we would like to call as ABCs of object storage use cases. The baseline is archive, where the requirements are moderate, both in terms of scale and performance. As you go down, you have applications or use cases like backup and content repositories, which demand increasingly high density of storage because the volume of the data stored is very high, and they are very sensitive to cost. The sensitivity to performance is not very high here because there is no end user sitting at the end of these requests. Throughput is important, though, to meet the backup windows. As you go up, in big data and cloud native apps, the latency has become important, as well as the scale of the object storage system in terms of the number of objects that can be supported. Now, having looked at some of the use cases, next, take a look at why object storage is becoming popular on premises. So first of all, enterprise applications are increasingly supporting consumption of object storage natively. And this is primarily driven by the need to be able to store data on the cloud for various reasons. But they are also finding that they are able to provide better semantics because of some of the new features that cloud storage offers, like worm or legal hold. Now, for security reasons, if you don't want to store data on the cloud storage, but want to consume some of these new features which are available from the cloud storage, which are relevant to some of these enterprise applications, an on-premises object store is quite useful. The next use case is cloud native apps, which are primarily driven or written for the cloud, but they also get run on premises. And as we know that cloud native apps primarily store their data or bulk of their data in object storage. So if you want to run them on premises, what do we do? Again, a native on-prem object storage will be very useful. The next reason why object storage is becoming relevant on premises is the scale and performance. Because of their flat namespace, the metadata overheads are insignificant to access or consume an object. At the same time, object storage also allows primitives by which large objects can be written through mechanisms like multi-part upload, or different versions of an object can be made by interfaces like object copies, which are making them popular on on-premises use cases. And lastly, it has a rich and evolving feature set. As I mentioned, S3 is the de facto standard here, and they keep adding features because they control the interface completely. Some of the features like website hosting and notifications, tagging, and rich user metadata are not easily available on access protocols like NFS and blocks. So if you want to use any of these, object storage naturally becomes a choice. Okay, so having looked at the significance of object storage on-prem, let's look at how a typical object storage system looks like. So here we have a block diagram of a typical object storage system, which is a scale-out shared nothing architecture, not specific to Nutanix. I think anybody who wants to build it will build it this way. At the very top, just under the clients, we have a bunch of load balancers whose job is to essentially bridge the client-facing network to the storage-facing network, which is shown in the second row underneath. And at the bottom, we have the storage subsystem, which is providing raw storage to the object store. Now, within the object store, which is a scale-out distributed system, you have an entity called S3 adapter, whose job is essentially to parse and interpret the HTTP S3 requests and translate it to a language that the internal object store subsystem can understand. So all of these components work in tandem together to provide a distributed scale-out object store system. The request will flow in from S3 clients to load balancer, from load balancer to one of the object controller nodes, which will first pass through an S3 adapter, followed by an object controller, and then it will end in the storage subsystem. Now, with that as a level set for how a distributed scale-out object store system looks like, let's first look into what does it take to benchmark such a system.
Thanks, Veer. Hi, everyone. I'm Arth. Let's get started on discussing the performance measurement and benchmarking of object storage subsystems. So while measuring the performance, there are two important metrics. First being the bandwidth of the object storage, and second being the latency of the object storage. Now, bandwidth is an important factor when we are talking about transferring large objects from the object storage subsystem, versus the latency, which is also known as time to first byte, is an important metric for the small object related activities, as that is going to be the leading factor of the effective performance seen by the clients. Now, with that in mind, there are a lot of existing object storage benchmarks available. You can categorize them in two primary categories. First is the single instance benchmarks. This typically run as a standalone binary on a VM or a host, and talk to the object storage endpoints to measure the performance. However, there is a very severe limitation that this kind of benchmark comes with, and that is the limited network bandwidth from the VM or the host that they are running on. If the distributed object storage system is capable of delivering very high throughput, these benchmarks will not be able to measure the performance and would rather be limited by the network bottleneck that they are hitting. To alleviate the situation, there are distributed benchmarks available as well, which can run on more than one VM or host and measure the performance of a distributed object store system. However, from our experience, we found that many of them are very complicated to set up, which would always require manual intervention or manual steps to get started on measuring the performance. Some of them are unstable at high throughputs. These tend to either crash or report incorrect errors, whereas the backend is able to perform much better than that. And some of them have limited performance even after allocating enough CPU and memory resources to these benchmark VMs. In this case, they would typically hit internal limitations of the benchmark tool itself and not be able to find the bottlenecks of the system that we are trying to measure the performance of. With these limitations in our mind, we finally decided to kind of design and develop our own benchmarking tool. We internally call it Poseidon Benchmark, and the way we have designed it, it improves on all the previously mentioned metric, right? So we have containerized it to ensure that it's easy to deploy on different types of the host operating systems as well as the images in case of VMs. For simulating different workload, we have also added a bunch of features. First being the configuration of data compressibility that the benchmark is generating. This allows us to benchmark different workloads by specifying how much compressible the data is. For example, if we are measuring the performance of a pre-compressed stream, something like video stream or audio stream, then we expect very little compressibility out of the data that is being returned to us. For example, something like 0 to 10% and around that range. However, if the objects being created on the object store are a result of text logs, we expect to see very, very high compressibility in 80% to 90% range. So this configuration allows us to simulate all these different kind of workloads that we are intending to optimize for. The second interesting feature that we have introduced is to specify the object size in terms of ranges rather than a fixed object size that we want to measure the performance on. And while some of the tools already allow this, what is unique is the ability to provide a distribution function for the different sizes of objects that are being created. In our case, we have ZipF and linear probability distribution for the object sizes, which allows us to simulate more realistic workload and I/O patterns. In terms of I/O patterns, what we allow you to configure is after creating, say, a set of objects, if you want to read them in the same order or random order or inverted order, we can configure all of this. So these three actually allow us to simulate all the workload that we have come across in a more streamlined fashion. The last and most important differentiation from other tools is the ability to bypass different components of the stack that Dheer just described. So here is how the overall stack would look like with the benchmarking tool deployed. So on the top, we have the benchmark itself, and the bottom half of this diagram essentially represents a typical object storage subsystem that we saw earlier. Now in the benchmark, you see there is a centralized controller which is responsible for accepting different workloads and kind of sending the appropriate requests to the actual workers, which are eventually responsible for generating the workload. The controller also periodically collects the statistics back from different worker instances and then shows them in an aggregated fashion. These workers can be scaled out as many to as many instances as we need to saturate the underlying storage subsystem, or rather the object storage. Now, when we talk about bypassing some of the layers, for example, if we want to bypass the load balancer to ensure that the load balancer themselves are not the bottleneck, we can configure the benchmark to directly talk to the S3 adapters that are sitting below the load balancers. Similarly, if we are interested in identifying any bottlenecks that may be present in the S3 adapter, we can decide to bypass that completely and directly configure the benchmark to talk to object controllers. Now notice that while talking to S3 adapter, we were using the HTTP or S3 APIs, whereas while talking to the object controller directly, we can talk in terms of internal RPCs that the object controllers understand today. Now, similarly, if you are interested in finding the bottlenecks of the object controller itself, we can in fact bypass the entire object related stack and directly talk to the underlying storage subsystem. This allows us to measure the baseline performance that the underlying storage subsystem can achieve and identify bottlenecks in every layer of our stack so that we can optimize each thing independently and transparently. Now, with this benchmarking tool, we were able to identify a lot of issues in our stack, and we'll go over one of the major design improvement that we have made using this the metric that we have collected from this benchmarking tool. So before going into the details of optimization, let's talk about a typical workflow of a create object request sent by an S3 client to the S3 adapter, right? So when the client requests to create a large object, the S3 adapter first processes the protocol specific headers, then starts doing the network read for a chunk of the payload that the S3 client is interested in creating the object with. Now, once enough data is read, an RPC is sent from the S3 adapter to the object controller, and the object controller starts calculating the checksum on the payload. Once the checksum is calculated, the data is sent to persist in the storage subsystem, and once the acknowledgement from the storage subsystem is received, it's forwarded back to the S3 adapter, and S3 adapter can start reading the next chunk of the payload. So this keeps on happening in a loop till we are able to drain all the chunks that the client has sent to the storage subsystem, and once everything is persisted, we send the final protocol response from the S3 adapter to the S3 client. And the client visible latency is the whole latency between this request and the response that you see on the screen. Now, the first optimization that we are going to discuss is the pipelining of some of the stages of this process. And as the name already suggests, this is essentially trying to overlap some of the activities that we perform to reduce the overall latency of the operation. So here is the first set of optimization that we do in terms of pipelining the request. So till the object controller receives the first chunk, everything remains the same. But instead of waiting for the checksum to complete, it immediately sends the request to persist the data to the storage subsystem along with starting the checksum calculation. Now, while these two kind of operate in parallel, the S3 adapter is waiting for the acknowledgement of the first chunk. Once both the checksum and data persistence operations are complete, we send the acknowledgement of the first chunk, and the S3 adapter can continue reading from the next chunk onwards. And this way we essentially hide the twofold latency of the checksum and data persistence with just one operation worth of latency. Notice that there is still some performance to be gained if we change the protocol between the S3 adapter and object controller a bit. And that is the second phase of the pipelining, where the acknowledgement of the receipt of the payload is different from the acknowledgement of persistence of the payload, which is combined in the future kind of chunks. But for the first chunk, as soon as the object controller receives the payload, it acknowledges the receipt so that the S3 adapter can start reading the next chunk while the previous chunk is being processed. At the same time, object controller is calculating the checksum. The data is being persisted for the chunk 1. The second chunk is already being read by the S3 adapter. And when the request lands on the object controller for the second chunk, we wait for the first chunk to be persisted and acknowledged. The acknowledgement of the receipt of chunk 2 and acknowledgement of persistence of chunk 1 is sent together to the S3 adapter, which then can start reading the chunk 3, and the whole process continues. Now, with this approach, we have essentially hidden the latency of all these operations in a single operation worth of duration. So this drastically reduces the response time for the client by doing pipelining in our stack. However, some of you might have already started noticing that we have shown equal sized blocks for different operations, but in reality, you expect them to operate at different speeds. So for example, reading a fixed amount of data from the network, calculating the checksum, and persisting that on a slow storage like hard drives will take different amount of time. A typical system with 10 gigabit network capability would be operating at around 1 gigabyte per second in terms of network read. The checksum, on the other hand, would typically, for example, for MD5 checksum, we would be able to typically run the checksum at around 400 to 500 megabytes per second per core. And for the data persistence on hard drives, we typically see 100 to 200 megabytes per second as the throughput, right? So these operations would ideally take different times depending on the system. So a more accurate representation of this protocol is represented here, where the network read is the smallest latency inducing factor versus the data persistence is the largest latency inducing factor here. And the checksum sits somewhere in between. Now with this, it's very clear that the overall latency of the response is still dominated by the slowest of the three, which is the data persistence operation. And we can actually optimize this by using another technique that we call reordering, where instead of processing this one chunk at a time throughout the system, we start operating on more than one chunk at a time, and at the end we kind of reorder all the responses back and send it back to the S3 adapter. So in this diagram we have color coded the different chunk so that we can easily identify which chunk we are talking about. So the chunk 1, which is the red color here, once the request is received by the object controller, same as the previous cases, we acknowledge back to the S3 adapter as well as issue the write for the storage subsystem. However, unlike previous approaches, we don't wait for the completion of the second of the first chunk to acknowledge the second chunk received from the object controller. So as soon as the second chunk is received by the object controller, the checksum and the data persistence, both operations are issued in parallel along with the receipt of the second chunk. Now here, if you notice, there are multiple operations outstanding on the storage subsystem at a given point in time, which allows us to hide the latency of the smallest operation of persisting the data. Notice that the checksum can't be overlapped in a similar fashion because the checksum has to be calculated on the entire stream, which means that we have to process one chunk at a time for calculating the checksum. However, on the storage subsystem part, we have more than one physical disk associated with the storage subsystem, which means that by doing more of these writes in parallel, we are not necessarily increasing the latency of the write itself. And that way we are able to hide the latency of these operations completely, and the effective bandwidth is now limited by the checksum calculation of this entire operation. And this way, the client visible latency of the whole operation is drastically reduced with these two approaches of doing pipelining and reordering. Now, to discuss some of the other issues that we found and fixed using this benchmark, I'll hand over the control to Subin.
Hi all, I'm Subin. So today I'm going to talk about the objects network architecture, some of the network issues identified in the network stack of objects, the tools we developed to identify those issues, the network optimizations we did to improve the performance, and finally the performance results. So I'll start with a network flow diagram. So as you can see, load balancer is the entry point to the objects. Any S3 request will reach the load balancer and will be forwarded to one of the object store components, the backend. So data will be processed there, and the processed data will finally land on the storage subsystem. So now let's have a look at the detailed diagram showing the software components along with some of the network infra pieces like switches and routers. Clearly, there are three networks in the object stack. First one is the client network exposed by the load balancer for clients to send the request. The second one is the objects network used by the load balancer to reach out to object storage backends. The third one is the storage network used to expose virtual disk to be consumed by the objects. These three networks are critical to the performance of object storage. Now, coming to the routing requirements, so there'll be two routings that can happen in the object stack. First one is from the client network to the objects network, and this will happen internally in the load balancer VM, minimizing any performance impacts. So the second possible routing is between the objects and the storage network. So this routing will be entirely handled at the L3 device. So naturally, packets will have to flow all the way up to the L3 device and come back for this routing to happen, and this will have a performance impact. So now let's move to some of the performance issues which were identified in the objects networking stack. I'll cover three of them here. The first one is the vHostNet CPU saturation. So with network-heavy workloads running on virtual machines with many CPUs, network bandwidth can be capped by the CPU available to the process handling network at the virtualization layer. So the Linux bottleneck implementation by default has only one socket corresponding to a tag device of a virtual NIC, and this will be mapped to a vHosted on the hypervisor for network handling. In our case, this single vHost thread was CPU saturated, limiting the network throughput available to the VM. The second possible issue is around cross network communication. So as explained in the previous slide, when objects in the storage are in different networks, data has to traverse from top of the rack switch to higher level switches and the L3 device to get routed. If the network pipe to the L3 device is not fat enough, we'll be hitting this bottleneck. Third issue is in terms of physical link saturation. So on high-end systems, the amount of network bandwidth required to saturate the storage bandwidth would be pretty high. And generally, this won't be achievable from a single NIC. So we can hit this issue as well. Now let's move to the tools we developed to debug the performance issues in objects. So Nutanix has a performance testing app called X-Ray, and we added our network debugging tools to it. So X-Ray is shipped as a downloadable virtual machine image along with a bunch of HCI performance and failure scenarios. The latest X-Ray 3.9, we even added the Poseidon benchmark-based objects performance scenarios. So the scenarios that are coming with the X-Ray are customizable. There's also a provision to add new scenarios as required. And for any automation, Ansible support is also provided. The test can be UI driven, and analysis or comparison of results are possible through UI. With the X-Ray integration of network performance debugging tools, we are able to drive large-scale Iperf scenarios through a single click from the UI. So now let's move to the Iperf scenarios implemented in the network debugging tool we developed. So a couple of them. Let's start with the node level Iperf chain. So here we'll be having Iperf connections between the hypervisor nodes. So the connections will be in a chain way, and the intention of this scenario is basically to identify the maximum physical network bandwidth available till the top of the rack switch. The second scenario is a VM level Iperf chain using a single network. So here we'll be running Iperf on virtual machines. So we'll be deploying one VM each in each host of the cluster, and Iperf connections will be in a chain way. The intention of this scenario is to identify the virtualization overheads. So by comparing this result with the node level Iperf result, we'll be able to figure out how much is the performance drop coming from the virtualization layer and what all tunings are required there. The third scenario is about VM level Iperf chain with dual network. So here also we'll deploy virtual machines, but each virtual machine will have two VNICs, both of them coming from two different VLANs. So, and the Iperf connections will be always across VLANs. The intention of the scenario is basically to identify what is the maximum routing bandwidth available in the network infrastructure. So this scenario can be used to identify cross-network communication issues. Apart from this, we also developed a scenario which mimics the exact network flow of objects. So the intention is again to identify the maximum network bandwidth possible and to identify the CPU required to drive that network. So now let's move to the solutions or optimizations we did to improve the network performance. The first issue was around vHostNet CPU saturation. So to avoid that bottleneck, we are using multi-queue VNICs. So with this, we'll be having multiple TXRX queues in the virtual unit driver, and these individual queues will be mapped to separate the host threads in the hypervisor, thereby limiting the CPU bottleneck due to a single thread handling the network. The second issue was around cross-network communication. So to avoid the issue, we recommend customers to deploy both storage and objects in the same network. So in exceptional cases where this is not possible, performance drop can be avoided by having a FATA pipe between the TOR and the L3 device, or by enabling L3 at the TOR switch. A third issue was around the physical link bottleneck. So on high-end systems, the bandwidth offered by a single link might not be sufficient to saturate the storage. So we'll have to use network bonding here. The Open vSwitch uplinks can be bonded to make sure that the entire storage bandwidth can be utilized. So now let's move to the performance results. So this particular chart is showing the VM network performance between the default and the optimized networks. So there are two charts here. One is showing the single Iperf instance, and the second one is showing 4 Iperf instances across 4 nodes. The single Iperf instance is showing a 35% improvement with the optimized network settings. And this is basically showing the gains when avoiding the CPU bottleneck at the vHostNet. The second one with 4 Iperf instances is showing a gain of 150%. And this is basically indicating the gains due to avoiding the CPU bottleneck at the vHostNet, and more importantly, the gains due to avoiding cross-network communication. The next slide shows the object storage performance improvements with the optimized network. So here we are doing 8 megabyte puts and gets at a high concurrency, and the throughput improvement for puts is around 35%, and for gets it's around 120%. By applying the network optimizations, we are able to move the bottleneck from network to storage and able to consume the storage bandwidth available in the cluster. That's the end of our presentation. Thank you.